last time, and on the back side we start talking about geometric series and how we can find sums of geometric series, or partial sums and sometimes infinite sums of geometric series. So I wouldn't expect you to know where this formula comes from, but you do need to be aware of it and especially how to use it. So if I've got the sum of a geometric series, so the sum of the first n terms of a geometric series, remember that's what S sub n stands for, that's the partial sum, the nth partial sum. So we start by plugging in a 1 and we stop when we plug in an n, so that for sure is a finite series. Then the sum of that, if it's geometric, the formula looks like this. We already know the one for the formula of an arithmetic one. That's the number of terms divided by 2, and then it's the first one plus the last one in parentheses. Okay? So this one is, we do need to know the first term, and then it's going to be, in the numerator, it's 1 minus r raised to the n. In the denominator, it's just 1 minus r. And this will work as long as r is not equal to 0 or 1. Okay? So as long as r is not equal to 0 or 1. Actually, I mean, they say that, but I guess it works if it were 0. That would be a pretty boring geometric series. The first term would be whatever the first term is, and if the common ratio is 0, what's the next term? If the common ratio is 0, that means you're multiplying by 0 every time. So you'd have, the first term would be whatever it is, and then the rest of them would be 0. Pretty boring there. Does anybody see why this wouldn't work if r is equal to 1? What's that? Why? Can't divide by 0. Okay? That would also be a pretty boring geometric series. In fact, we wouldn't even have to think of it as geometric. If the common ratio were 1, and let's say the first term was 7, what's the next term? 7. 7. Multiplied by 1 every time. It's not really geometric. It would be arithmetic. They'd all be constant. Okay? And that's easy to find the sum for. Okay, so let's take a look at a couple of these. This is the sum of this many terms right here. Now, the nice thing about this is you can just go through and you can count them. We could double check this by plugging this into our calculator, but we want to make note of this. In this formula, here's what you need. You need to know the first term, you need to know the common ratio, and you need to know n. So similar to the sum of an arithmetic series, we need to know three things. We need to know the first term, we need to know the common ratio, and we need to know n. We need to know how many we're adding up. So on a problem like this, it's fairly easy to go through and count. We've got 1, 2, 3, 4, 5, 6, 7. So on this one, n is equal to 7. We know the first term is 1, so that's kind of nice. And then the other thing that we need to know on this one is we need to know the common ratio. Well, how do we go from one term to the next term? Multiply by positive 3, right? It's getting larger. So we know r is equal to 3. So let's plug these into the formula. So the sum of the first 7 terms is going to be the first term, 1. And then we're going to multiply that by a fraction. It's 1 minus the common ratio raised to the 7th over 1 minus whatever the common ratio is. So on this problem, the only other thing that we have to plug in is a 3. So we'll put a 3 right there and right there. So the numerator is 1 minus 3 to the 7th, and the denominator is negative 2. That's it. So we're going to plug this into our calculator. If you do it as one single expression, you're going to type the numerator in parentheses, 1 minus 3 to the 7th, and then we're going to divide by negative 2. And you'll notice that the numerator is going to be 1 minus a huge negative number. So the top's going to be negative. But the bottom's also negative, so our answer is going to turn out to be positive, as you would expect because we're adding up a bunch of positive numbers. Okay? Any questions? Okay, what'd you get for an answer? 1,093. 1,093. Okay? There we go. If you type something in wrong, you're going to get the wrong answer. If you don't put parentheses around it and you do it as one single expression, you're definitely going to get the wrong answer. Okay? But there's our answer right there. And if we add these up, that looks like a little, that's about 300 or so. So we're going to be about 1,000, a little bit more than 1,000. Looks pretty reasonable. Okay, if we have time, we'll come back at the end and we'll do this one on the calculator too. Or we'll check a couple on the calculator and how we can type that in there. Okay, any questions? Okay, let's take a look at the next one. The problem here is a couple of things. Remember, we need to know what the first term is. So on this one, we know the first term is 1/2. The common ratio isn't too hard to figure out. Take any term, divide it by the one before it. What are we multiplying by every time? What's the common ratio here? Common ratio is also 1/2. Here's the trouble. We've got to figure out what term we're on right here. Okay, we need to know, gosh, is this the 6th term? Is it the 19th term? Which term is it? Okay, so sometimes you're going to have to come up with a formula. So this term right here, 1/256, is equal to the first term times n minus 1 common ratios of 1/2. We want to figure out what n we plug in for that. So I'm going to start solving for this. I'm going to multiply both sides by 2. That's going to be 1/128 equals 1/2 raised to the n minus 1. Whoops. I'm going to write this as, so I'll write it down here. This is going to be 1/128. I'm going to write this as 1/2 to the n times 1/2 to the negative 1. Is that right? Remember, I can break this up into two parts. 1/2 to the n and 1/2 to the negative 1. Okay, what does the negative mean? Okay, negative means you can flip it over. It means reciprocal, right? Okay, so if I come up here, this is 1/128 equals 1/2 to the n times by 2. So if I want to get rid of that 2, I'm going to multiply both sides by 1/2. So this is 1/256 equals 1/2 raised to the n. Ideas here? What's that? Okay, kind of the right idea, but it wouldn't be a square root because we want to get rid of raising that to the nth power. Nth root. Okay, the problem is we don't know what n is, right? Okay, take a good look at this. What type of equation is this? I heard somebody say, Hop, what is it? Exponential. How do you undo an exponent? How do you get that exponent down where we can work with it? A log. You can take a log, okay? Now, we could take a log base 1/2 of both sides, and this isn't the only way to solve it, but this is a good review. Let's do the ln of both sides. Okay, that's going to give me the ln of 1/256 equals n times the ln of 1/2. So if I divide both sides by the ln of 1/2, that's going to tell me what n is. And that you can type into your calculator. Ln of 1/256 divided by the ln of 1/2. It is 8. Okay. Okay. So you get n is equal to 8, and then we can plug it into the formula. I do want to show you this. Everybody watch, please. Okay, right here, I've got 1/256 equals 1/2 raised to the n. One way I could change that into a little bit better format is, if I flip this one over, couldn't I flip that one over? And then just take the ln of both sides? Or take the log base 2 of both sides if you wanted to. But what's the problem with taking the log base 2? Not on your calculator, okay? All right, so let's see what we get here for an answer. On this one, we're going to have the sum of the first 8 terms is going to be 1/2, and then it's going to be times 1 minus 1/2 raised to the 8th over 1 minus 1/2. And let's take a good look at this. This right here would be 1/2, right? And that's 1/2. Can't I cancel this with this? So wouldn't the sum of the first 8 terms just be 1 minus 1/2 raised to the 8th? Good there? Type that into your calculator. You're going to get some point, probably 0.9 something. And you might be able to change it to a fraction. If you hit math, change to a fraction, you should get 255, 256. Is that right? Okay. All right. Any questions? Okay. So as long as you can identify those 3 things, you're in good shape. You've got to know the first term, you've got to know the common ratio, and you've got to know how many terms we're trying to add up. Okay. Take a look at this one right here. Okay. This one's kind of nice. Okay. On this one, we started out with a different index, but we do know the first term, don't we? Excuse me. Thank you. What's the first term? It's what you get when you plug in a 1. If you plug in a 1, it's 2. The first term is 2. Can you look at it and can you tell what the common ratio is? Please say yes. Yeah, it's written as an exponential, so the base of the exponential is the common ratio. So that's 0.4. And can you look at it and tell how many terms we're trying to add up? Yeah, we're trying to add up 12 of them because we started at 1 and went to 12. Remember that little technique that we talked about yesterday? We said if you want to figure this out, you could take this term right, or this index right here, subtract 1 less than that lower limit right there. That would be 12 subtract 0. So there are 12 terms there. So the sum of the first 12 terms is going to be the first term, which is 2, 1 minus 0.4 raised to the 12th over 1 minus 0.4. And then as long as we type that into the calculator correctly, we should get the right answer. And the nice thing about this is it's written as decimals, so we're definitely going to use a calculator on this one. So let me clear this off, and I'm going to do 2 parentheses, 1 minus 0.4 raised to the 12th, close the parentheses, and then I'm going to do divide by. Okay, to make sure I type this in correctly, I could just write 0.6, but I'm going to do 1 minus 0.4. That should be the structure of every one of those problems that you type in. Hit enter, and there we are right there. Now, so 3.3327 and so forth, we could just double check this and see if we could make this a fraction. Maybe it would turn into a fraction. It doesn't. So it's a long enough and an ugly enough decimal that it's not going to give that to us. Okay. So we're going to say it's approximately 3.333. Okay, any questions? Okay, good? Okay, I want you to look at the next one because this one's a little bit different. Okay, we need to identify 3 things. We need to know the first term. What's the first term? 1/2. Common ratio. Just like the one above it, right? Isn't that 1/2 also? Okay. And then we've got this guy right here. We need to know how many terms are we adding up? Well, it just says n. I mean, if this is the formula for the nth term, if I plug in a 1, that gives me a 1/2. If I plug in a 2, that gives me a 1/4. So this literally is the nth term. This is exactly how many terms we're adding up. So the problem with this one is the answer to this is going to be a formula rather than an actual number like all these others have given us. Okay? Like this one up here gave us 255, 256 if we wrote it down as a fraction. Good? Okay, so here's what we do. We're going to go through and we're going to do this exactly the same as we would, and we're going to see what ends up happening. So the sum of the first n terms, which let me change this back to green. The sum of the first n terms is the first term, which is 1/2, times 1 minus the common ratio raised to the n over 1 minus the common ratio. Now, like I said before, the denominator works out to be 1/2. The denominator works out to be 1/2. So I'm going to cancel this with this, and we end up with this right here. Here's our formula. So the answer is 1 minus 1/2 raised to the n. So the sum of the first n terms is this expression right here. And if this were a problem in the textbook and it were odd and you looked it up in the back of the book, this would be the answer, okay? And this idea is going to be helpful right here, okay, in making sense of some of the stuff that we're going to do next. But I want you to take a look at this. Would this formula work for this one right here? The sum of the first 8 terms that we had here. If I put an 8 right here, I put an 8 right there. Isn't that what we ended up with right there? So the cool thing about this is, what if I wanted to find the sum of the first one term? I want to find the first partial sum. What do I plug in here? A 1. And this would be 1 minus 1/2. I get 1/2. Isn't that the first partial sum? Yeah. If I want to find the second partial sum, okay, the sum of these two terms right here. I mean, we can tell that it's 3/4, but take a look. This would be 1 minus 1/2 squared. 1/2 squared is 1/4. What's 1 minus 1/4? 3/4. Okay? So that formula does work, and that's going to come in handy. Okay, are there any questions about those? Okay, let's take a look at the next one, or the next set of these problems right here. So all these examples that we did right here, these first 4 problems right here, these are what we call finite series. We're going to add up to a certain point, and then we're going to stop adding. And it makes sense that if you're going to stop, even if you add up 1,000 terms, you could be here all day, but you could get a number answer for that. Okay, you could definitely add up a finite series. Okay, if it's an infinite series, that seems a little bit weird that we'd actually get a number answer, but it's possible with some particular types of series to get a number answer if we go on and add forever, okay, and never stop. So that's called an infinite series. So let's take a look at this one right here. And what we want to do first is we want to figure out which ones would have a sum and which ones wouldn't. So let's take a look at 5 to the k. And we're going to start by plugging in a 1, and we're going to stop. Well, we're never going to stop because that upper limit is infinity. So the first term is a 5, the second term is a 25, then a 125, and then the next one's a 625, and then we continue going on and on and on and on. Okay? Are we going to be able to say, well, gosh, we can stop right here and this adds up to this particular number? Not on that one. How about this one right here? This one would be, if I plug in a 1, I get a -2. If I plug in a 2, I get a 4. Then I subtract 8. Then I add 16. Then I subtract 32, and so forth. Are we going to be able to take those and say, you know what, this adds up to this particular number right here? Not on that either. Okay, but let's think about this one right here. Okay, because this one is fundamentally different than the other two. So I'm going to change colors here, and let's write out a couple of these. If I plug in a 1, I get a 1/2. If I plug in a 2, I get a 1/4. Then a 1/8, then a 1/16, and it's looking really familiar now. Okay, and it just goes on and on and on. Okay, we get that term that's 1/256. The next one is 1/512. The next one is 1/1024, and then we just keep going on and on and on. Okay, what's the difference between these terms right here, as we continue adding and adding and adding, and these terms right here in this series? What's happening to these numbers, and what's happening to these numbers? Every term gets bigger. Every term gets bigger in absolute value. What happens to these terms? They get smaller. Okay? In fact, how small are these going to get? They're going to get super small. They're going to get really, really, really small. If you want to check and see, type into your calculator, type in 1/2, put it in parentheses, and raise it to the 100th. 1/2 to the 100th. What does your calculator say it is? 10 to the -31st. So that means a decimal, okay, 30 zeros, and then you'd see a 7. Okay? So a tiny, tiny number. Okay? So I'm going to show you a little demonstration. Okay, here are the partial sums. So I've got a piece of paper here, just one piece of paper. All right, and what I'm going to do is I'm going to take this, and we're going to keep track of the partial sums. So what's the first term in the series there? It's 1/2, right? So I'm going to take this, and I'm going to tear it in half. Here's a half. Okay, so there's the first partial sum. The first partial sum is 1/2. Okay, second partial sum, I need to add 1/4 to it, right? So I'm going to tear what I had in my hand in half, and I'm going to put it over here. So how much is in this stack right here? What's my second partial sum? 3/4. I've got 3/4 of the piece of paper right here. How much do I have in my hand? I've got 1/4 left. So the third partial sum, I need to add 1/8. 7/8 over here, I've only got 1/8 left. Okay? 15/16. Okay, and if I keep doing this, this is going to be 31/31, or 31/32, 63/64. Okay, this is 128th of a piece of paper. So what I have here is 127 128ths. The next one is 255 256. Okay, here's a 512ths of a piece of paper. So this is 511 512ths. Okay, what's going to happen if I keep doing this forever? Okay, so I have a little, this is so small I can hardly tear it anymore. Okay, is there any way I'm going to get more than one piece of paper in this stack right here? Nope. So if I kept doing this, if I talked about finding what the limit of this process was, if I continued this forever, okay, I'm going to start splitting atoms and I'm going to put them over here. But eventually, if I let this go forever, but does everybody agree that essentially I would have one piece of paper in this stack right here? Okay? So, if I went on forever, this actually adds up to 1. That pattern of adding 1/2 plus 1/4 plus 1/8 and so forth adds up to 1. Okay? So we want to keep track of a couple of things. In order for an infinite geometric series to have a sum, the ratio has to be less than 1 in absolute value. And the reason it's got to be less than 1 in absolute value, we can see right here. If it's bigger than 1, what happens to the numbers? They get bigger. If it's less than 1 in absolute value, they get smaller. Okay? They end up approaching 0, okay, in this nice geometric way, so it can actually have a sum. Okay? If an infinite geometric series has a sum, then we say it converges. So the example that we just did, that converges to 1. The partial sums converge to 1. And if it doesn't converge, then we say it diverges. Okay? So, if we look at this formula right here and we think about this for just a second, what happens in this formula if I have 1 minus 1 minus r to the n over 1 minus r? What happens if the common ratio is a number less than 1 in absolute value? Like what if it's 1/2? What happens to r to the n? What happens to these terms that we're plugging in and we take r? This gets smaller and smaller, okay? So what does the top turn into? 1 minus a number that gets smaller and smaller and smaller turns into a 1. And the bottom is just 1 minus r. So that means the sum of an infinite geometric series, and you'll notice that we've just got a big capital S here, is just the first term over 1 minus r. And this formula works as long as the common ratio is less than 1 in absolute value. So it can be negative 0.2, positive 0.3, it can be 1/2, it can be 7/8, it can be negative 0.999. As long as it's less than 1 in absolute value, it's got a sum. Okay? So what is, on this problem right here, what's the first term? 1/2. Over 1 minus the common ratio. What was the common ratio again? 1/2. So this is 1/2 over 1/2. So we end up with 1. Okay? That's how that formula produces the answer. Okay? Now the cool thing about an infinite geometric series, even though it's a more complicated idea, remember up here we had to have three different things. You had to know the first term, the common ratio, and you had to know what n was. Well, on this one, all you need to know is what's a and what's r. That's it. So we can prove some kind of surprising results with this. We've already talked about this idea, but remember this one right here? This one was 3/10, 3/100, 3/1000, 300,000, or 3/10,000. Okay, does anybody remember what that added up to? 1/3. Adds up to 1/3. And we can actually prove that now using this formula. Okay, what's the first term? 0.3. What's the common ratio? 1/10. It's 1/10, 1/10. And I'll do it as a decimal. So the sum of this should be, the first term is 0.3. 1 minus the common ratio of 0.1. So this is 0.3 over 0.9. What's 0.3 over 0.9? 1/3. Exactly 1/3. Okay? Any questions? Okay, little mind-blowing. Okay, let's take a look at another one. Let's look at this guy right here. Let's prove that 0.99 repeated. Okay, just a bunch of nines going on forever. Let's prove that that's actually equal to 1. Seems a little bit counterintuitive. Okay, but here's how we're going to do this. So we're going to take the first term here, and we're going to think of that as 0.9 plus 0.09 plus 0.009 plus 0.009. And we're just going to let that go on forever. If you want to think of it as a fraction, this is 9/10, this is 9/100, this is 9/1000, this is 9/10,000. That might be easier to see what the common ratio is. So the first term is 0.9. What's the common ratio? 1/10. So the formula says that the sum of this is going to be the first term, which is 0.9, over 1 minus the common ratio of 0.1. So that's 0.9 over 0.9. And what is 0.9 over 0.9? 1. So 0.9 repeated, let that go on forever, it's equal to 1. Okay? We'll argue about stuff like this when you get to calculus. Because somebody's going to say, well, wait a minute. You never actually equal to 1 because there's always that, we didn't make that last digit 0 so we could round it up and stuff like that. Okay? How close do you want to get to 1? We could just continue with the 9s until you're as close as you want to be to 1. So it's effectively 1, or its limit is 1 is what we talk about. Okay? It's the limit of the process. If you stopped at any point, if you stopped adding, it wouldn't equal to 1. But the fact that you're going to go on forever means it would equal 1. Okay? All right, so let's take a look at a couple more problems. Okay, let's take a look at this one right here. Does this converge to an answer because it's an infinite geometric series, or does it diverge? Okay, why does it diverge? Okay, r is greater than 1 in absolute value. Okay, if I do 3/2, okay, it's not less than 1 in absolute value. Okay, so that one diverges. Okay, let's check this next one. I've got 2 4/3, 8/9, negative 16/27, 32/81, plus minus. Okay. First of all, we'd want to check and see what the common ratio is, right? So on this one, I'm going to take negative 4/3 and I'm going to divide it by 2 over 1. I'm going to flip that over, so that's going to be 1/2. I'm going to cancel here, so I end up with negative 2/3. That's the ratio between the first two. Let's pick another couple. Let's pick 32/81 and put it over negative 16 over 27. So So I'm going to flip that over. So I'm going to have negative 27 on the top and 16 on the bottom. That's going to give me a 2 on the top. And I can cancel the 27 with the 81. That's going to be a 3. And notice I've still got this negative hanging around here. So that's going to be negative 2 on the top, 3 on the bottom. Do we have a geometric series? Yes, we do. So the common ratio is negative 2/3. Converge or diverge? Converge. Okay? Because if I put that in absolute value, it's less than 1. Absolute value of negative 2/3 is less than 1. So all I need to do is find the sum. Only 2 things are needed. The first term is 2. 1 minus the common ratio. Let's make sure we get this right. That's negative 2/3. So that means I'm going to be adding 2/3. So this is 2 over. This would be 5/3. Correct me if I'm wrong. Flip that over. So that's going to be 3/5. So my answer here is 6/5. Now somebody do me a favor. Type that into your calculator if you need to. 6 divided by 5, what do you get? 1.2. Okay? So as a decimal, it's 1.2. As a fraction, it's 6/5. Okay, are there any questions? Okay, we've got enough time. Grab your calculator. We're going to take a look at a couple of these. So on the calculator, here's what we're going to do. Let's see. Yeah, let's do this one right here. Okay. The nth term on this one would be the first term, and what's the common ratio? This one right here. Let's just check this answer. Okay, so it's negative 2/3, and this is going to be raised to the n minus 1, right? So on your calculator, here's what we're going to do. Okay, and I'm going to build this from scratch just so we've got that. Okay, so we hit second list. Okay, there's the sequence. We don't want that yet. We want sum. Now I want to tell it what sequence to do. So I'm going to tell it to grab that sequence command. And then I'm going to type in the sequence. This is the sequence that I'm going to type in. I'm going to type in a 2, then a set of parentheses, a negative 2 divided by 3, close the parentheses, and I'm going to raise that to, I've got to be kind of careful here. I've got to make sure that this is the entire exponent, so I'm going to do x minus 1, close parentheses. First term, common ratio raised to the x minus 1, put a comma. If you've been paying attention, what goes next? The variable. What variable are we using for the index? X. Comma. Where are we going to start? Start by plugging in a 1. Okay, now where are we going to stop? We're never going to stop. Now, does your calculator know how to do that? No. So let's do this. Let's have it add up, let's say 50 terms. These terms are going to get pretty small after 50 terms. If I just hit enter, it's going to work for a while. You may have a faster processor or an updated operating system. This is going to take a while to add this up. Okay, think about what it's doing. 50 terms. It calculated every one of those and added them up, and what do we get? Well, look at that. Okay, all the way out to there. Now, if those 9s continued by that same argument, okay, we'd have to round this up a little bit, and it would be 1.2, wouldn't it? Okay? So if I recall that command and I change this to just 100, okay, that's going to make this work really hard. It may even overload this calculator. But it's going to take about twice as long to do that, and it's going to spit out an answer. Yeah, hopefully. While it's doing that, let's think about how we're going to do this one right here to confirm that answer. What is it? You said 1.2? Mine's still working. This operating system's probably, well, there you go. Okay. Much older, takes a little longer, but it still spits out a 1.2. Now, does that mean if you just add up the first 100 terms, it's exactly 1.2? No, what it means is we've overwhelmed the calculator. For all intents and purposes, for all the storage the calculator has, probably 100 decimal places, it's accurate out to 100 decimal places, and it just said, look, if I've got a 1.1 all nines, I'm just going to make that a 1.2, and we're going to call it effectively a 1.2. Got it? Okay. Would you put this one in your calculator? It's a finite one. It'll do that pretty quickly. Put that one in your calculator. It's going to add up the first 8 terms of that 1/2, 1/4, 1/8, 1/16, and so forth. It should give you a kind of ugly looking decimal. See if you can change it to a fraction and see if it confirms the answer we got a minute ago. What'd you get as a decimal? 0.996. And if you change that to a fraction, what did it say? 255, 256. Okay, so did we get it right? And you could do something like this. This is a finite one, so it's definitely going to have an answer there. Okay, are there any questions? Okay, this is not on your paper, so if you just watch, please. Okay, don't be surprised if when you take the end of the year test, if you take that SAGE test, that there's something like this on there. The people who made that test and the people who came up with the Common Core for math, they like pattern spotting and different things like that. So if you have basic tools like how to deal with an arithmetic sequence, how to deal with a geometric sequence or series, maybe we can take a problem that's a little bit more complicated than that and figure out what the answer is with the tools that we already know. So here's the problem. It says a deposit of $50 is made on the first day of each month in the savings account that pays 6% compounded monthly. Okay, what is the balance of this annuity, okay, or in other words, this account, if you want to think of it that way, at the end of 2 years? So at the end of 24 months, okay? So the first thing we'd have to do is we'd have to remember the formula for compound interest, and I'm hoping somebody in here remembers the formula for compound interest. PERT is the one for continuous compound interest. Does anybody remember what it is for just compound interest? R over N raised to the NT, okay? So N is the number of times it's compounded per period or usually per year. So we're going to do this one this way. We're going to do this in months, okay? And let's take 6% and let's figure out how much they're paying interest per month. So this is 6% per month, and there are 12 months in a year, so we're going to divide by 12. So on your calculator, or maybe you can figure this out, what is 0.06 divided by 12? Okay, 0.005, okay? So this is the interest rate, okay? There's our R. This is our time in months, and we're going to put $50 in there, okay? So what's going to happen to that first one is this. So that first deposit, it's going to sit in there for, we put in $50. It's paid, 1 plus 0.005. There's the 100% of what we put in plus the interest. How many times are they going to pay interest? Okay, on this over 2 years. They're going to pay it 24 times. Okay, so there's the first deposit. Okay, so think of that as January 1st. 2 years go by, they're going to pay us this much. That much is going to be in the account from that one. Okay, for the second deposit, we put in $50. They're going to pay us this much interest. But because we put it in at the beginning of February and not the beginning of January, how many times are they going to pay interest on this? 23 times, right? Third deposit. So our March 1st deposit, we put in $50. They're going to pay this much interest. How many times are they going to pay that? 22 times. So if we continued this, not really a factorial, but we're gonna get this written down. So the 23rd deposit, So that would be November 1st of the second year. We're going to put in $50. They're going to pay us this much interest, but how many times are they going to pay us that interest? Okay, they're going to pay it to us at the beginning of December, 30 days later, and then another at the very end of December, or January 1st. Does that make sense? So they're going to give us 2. Pay us interest twice. Okay, and what about the 24th deposit? So this is January of year 1. This is February of year 1. Year 1. And this is November of year 2, and this is December of year 2. $50, 1 plus 0.005. How many times are they going to pay us interest? Just once. Okay, now this is written backwards, but does this look familiar? Isn't this a geometric series? Okay, isn't this the sum from n equals 1 all the way to 24 of 50, 1.005 raised to the n? And what's the formula for the sum of the first 24? A, 1 minus r, raised to the 24 over 1 minus r. Okay? All you have to do is figure out what's the common ratio. You might be able to look at it and tell that. And what's the first term. Okay? All right, I'll leave that for you to figure out. Please come with this one figured out tomorrow. Tell me how much money's in that account. You've got everything you need to do the entire assignment on 9-3, so go ahead and do that. Make sure you have that done tomorrow when you come to class. Where do you find the problem numbers? Online, okay?